Hello there, and welcome to the final video in our mini-series on the elevation factor. My name is Tom Meyer, and this is a production of the American Association for Geodetic Surveying. The purpose of this video is really twofold. The first is to introduce a couple of formulas that will allow us to reduce slope distances directly without using the elevation factor. And the other is to compare various types of horizontal distances that we might reduce with the elevation factor. Up until now, we've only thought about the elevation factor, but we know that exactly which distance is being reduced is a little ambiguous. We could reduce the horizontal distance from the forwards, from the observation station to the forward station. We could reduce the reciprocal distance if we were running bidirectionally, like for a control survey. We could reduce the average distance. There's a lot of things we could reduce. And so what we're going to do is take a look at all of those and see how they compare. And then I'll show you these two formulas that go from the slope distance directly to the ellipsoid, and then we'll compare everything and see what we can see. Here are the things we're going to do. Using the elevation factor, we'll reduce the slope distance itself, the horizontal distance from A to B. And really, the thing to know here is that in our testing, A is always lower than B. Then we'll also test going from B to A. Those are different. And the average horizontal distance, the average of those two horizontals. And then the two direct formulas. Here's the notation we're going to be using. I've changed Gaussian radius of curvature in this video from G to R, otherwise I think everything should be familiar. The first of our two distances takes slope distance directly to the chord that you see here. D sub E is the distance on the ellipsoid that we want, and this formula takes us to the chord instead of to the curve, but it turns out it's going to work very well anyway. The formula is here. It's a little bit more complicated than for the elevation factor, but it doesn't pose any challenges to programming languages or spreadsheets. It's still pretty simple. I want to ask the question, what happens to this formula if the two stations are at the same height? So HA equals HB. Well, the formula is here at the top. Setting HA equal to HB, the term here that's the difference of those two, well, that goes to 0, and we're left with ds squared over r plus h squared, having substitute r plus h for RA and RB, because those two would become equal when HA is equal to HB. So all those terms are under a square root, so all the squareds just vanish, and then with a little rearranging, we see that this chord distance is the slope distance times r over r plus h, but that second term, the r over r plus h, that's the elevation factor. So what we understand then is that this formula that goes to the chord is simply a generalization of the elevation factor formula when the two stations are at different heights. So there's nothing mysterious or exotic happening here. It's just a generalization. The second of the two formulas takes our slope distance to the arc that we want. It's going to reduce it to a circular arc. Formula is here, and the terms over in the that are the argument to the cosine, that's just a straightforward application of the law of the cosines to this figure here, where theta is the angle between r and r. And bear in mind that in reality, theta would be an incredibly small angle. R is on the order of 6.3 million. And ds would typically be a couple hundred at the most, maybe, kinda. So I can't draw it like that. If I drew it to scale, the two sides of this triangle would lay on top of each other for pixel. So I've drawn it as if theta is like, what, 30 degrees or something, but in reality it would be incredibly close to 0. When we're computing with finite precision arithmetic, as we do with computers, we want to avoid doing arithmetic with very large numbers. So here we see RA, RB as squareds and then their product. We're taking numbers here that are on the order of magnitude of 6.3 million and we're squaring them, we're getting extremely large numbers. This is actually causing some truncation and round-off error in the computer, which I'll show you in just a second. So let's do a little bit of algebra. We can split the argument to the arc cosine apart and write it as you see at the bottom. So RA divided by RB, that's close to 1. RB over RA, also close to 1. The term that we're subtracting, we do not multiply the DS's together to get D squared and then the RA times RB because that would be squaring these two large numbers. So instead, we're going to compute DS divided by RA, which is a number actually rather close to 0. Same for DS over RB. So we've got basically 1 plus 1 minus something close to 0. This is going to be a number very, very, very close, just slightly less than 2. And so when we divide it by we multiply by half, we get a number that's just slightly less than 1. Let me compare the error regime for the two formulas. On the left, this is the histogram of the errors that we get from the formula where we take the square of those large numbers. It is very close to being centered at 0. And the standard deviation is 0.005 millimeters. And the error spans from a negative plus and minus 0.014. On the right, this is from the second formula, which doesn't involve all those squareds. Likewise, centered at 0, but the standard deviation is smaller. It's 0.003. And the error span plus and minus 0.01 millimeters. So this is just better. These numbers, these numbers are incredibly small. We're talking about thousandths of a millimeter here, or 1/100th of a millimeter. And so from a pragmatic perspective, does this really matter? Well, pragmatically, probably not. But the second formula is simply better. There's no reason not to use it. So we should. Again, let's ask ourselves what happens if the two stations are at the same height. Well, we plug in RA equal RB, which is equal to R plus H. This formula reduces down then with those substitutions to what you see at the bottom. Now, the term that's the argument to the arc cosine, well, we can actually get that from the law of sines. We can see that the cosine of theta is equal to 1 minus d squared, ds squared, over 2 times the quantity r plus h squared. And so we can substitute cosine of theta for this term on the right. That gives us r times the arc cosine of the cosine of theta, which of course is just r theta. So this formula boils down to d equal r theta, the famous formula that gives us the length of a circular arc segment given the radius of the circle and the angle subtended. Once again, we see this formula is nothing weird or exotic. It's just a generalization of d equal r theta. For a testing algorithm, then, here's the way we're going to initialize it. This is very similar to what we did in the previous video. We're going to give ourselves a starting station A. It'll start at 20 degrees north and end at 71¼ degrees north. That spans the United States from Hawaii to the North Shore of Alaska. We'll set the longitude equal to 0. The longitude plays no role in these computations, so it doesn't matter what value we pick. We have to pick something, so I'll pick 0. We'll let the testing heights vary from 0 to 2,000 meters, and we'll set the length of the baseline on the ellipsoid to be 1,000 meters. Very long line here. We'll test at 3 azimuths, 0, 45, and 90 degrees. And the forward station will be a fixed 100 meters higher than the observation station in all cases. For the cases that we are going to do reductions with the elevation factor, the algorithm goes like this. We start with A, the distance on the ellipsoid, and the azimuth to the forward station. Using the direct problem of geodesics, we will calculate B's coordinates, longitude and latitude. We will set A's coordinates to be the testing height h that varies from 0 to 2,000 meters. And then we'll set B's height to be that of A plus delta h, the constant 100 meters. Now we've got A and B in longitude, latitude, and height coordinates, so we will just convert those to XYZ geocentric Cartesian coordinates in the usual way. We can then calculate the slope distance, which is just the straight line distance between A and B in these Cartesian coordinates, using the three-dimensional version of Pythagoras' formula. Then we will compute the Gaussian radius of curvature R at the average of the latitudes of the two stations. And from that, we will compute the elevation factor as usual. The distance reduced on the ellipsoid is this ds, the slope distance, whatever distance it is that we are reducing, multiplied by the elevation factor. The error then is the reduced distance minus d0, which is a fixed 1,000 meters. In every case, we're supposed to be reducing back to d0. For the cases in which we are directly reducing the slope distances, we'll just apply the two formulas that you saw before. And again, the error will be the reduced distance minus the d0 distance. How do we get our horizontal distances? That's a little bit complex, and so I want to walk you through it with a picture to get started. What we're going to think about here is the horizontal distance from B to A. We have B's coordinates in XYZ and in longitude, latitude, and height. That is what we need to create a local topocentric geodetic east-north-up coordinate system whose origin is at B. That creates a horizontal plane centered at B. That plane is perpendicular to the normal of the reference ellipsoid. Once we have that coordinate system, we convert A into that coordinate system. That is going to enable us to compute the horizontal distance from B to A. So let's start with the horizontal distance from A to B. We will get B XYZ coordinates and convert those to east, north, up in A's coordinate system. Then the distance from A to B, the horizontal distance from A to B, is just the easting of B squared plus the northing of B squared. Omit the height term because it's a horizontal distance, and we don't need A's coordinates because they are identically 0. This first bullet is in A's coordinate system, and A is the origin of its own east-north-up system, so its coordinates are 0, 0, 0. So then the reduced distance is the horizontal distance multiplied by the elevation factor. Same logic follows for B, but swapping A's and B's. And then finally, once we have both of those horizontal distances, compute their average, reduce that average distance, and in all cases, the error is the reduced distance minus d sub 0. All right. Well, let's see what happens. Let's start by taking a look at what we get when we reduce the average horizontal distance down to the ellipsoid. So we've got these three planes. Each plane is a different azimuth. Left is azimuth of 0 running north-south. Middle is an azimuth of 45. Right is an azimuth of 90 running to the east. The errors are in millimeters, and we see that for 0 and 90 degrees, the error is bounded by 1 millimeter. So for 0, it goes from 1 millimeter down to 0. For 90, it goes from 0 down to negative 1 millimeter. So on a 1,000-meter line, with the forward station 100 meters higher, the error is never worse than 1 millimeter. That's a fantastic result. So this reducing using this horizontal distance, it fits well with our notion of what the theory wants. It does, in fact, work very, very well. Scrutinizing the ISO lines, these are error ISO lines a little bit more, we see that the error decreases as we get closer to the pole. Notice that the 0 error is way up here, tucked up in the corner. You could just barely see it. This makes sense because we're using the Gaussian radius of curvature as the value for R. But the Gaussian radius of curvature is the geometric mean of n and m. And all three of these values, n, m, and the Gaussian radius of curvature g, they all are equal to each other at the pole, and they're the most different at the equator. And so we would anticipate error would reduce as we increase in latitude, and it does. It's exactly what we see. It also increases with height. This is, again, hardly surprising. We know that this horizontal distance is going to match the corresponding distance on the ellipsoid best when the stations are on the ellipsoid, and the further away you get from it, the less well it matches. So the error increases with increasing height, completely anticipatable. When we draw our attention to the center pane, this is an azimuth of 45. Well, this is where G almost exactly equals the radius of curvature in the normal section for 45 degrees. And look at the errors. This is 10 thousandths. This is basically 3 thousandths of a millimeter down to 4 thousandths. And this is essentially zero. And if we had taken the azimuth ever so slightly northwards of 45, like 44.95, these errors would straddle zero. Yeah. So this works extremely well. Now, you might wonder, why are the errors all positive for 0 and they're negative for 90? Well, it's because the radius of curvature is, the Gaussian radius of curvature is greater than m for, well, it just is. The Gaussian radius of curvature is always greater than m, except when they're exactly equal at the poles. And it's always less than n unless you're at the poles. So that's where the signs are coming from. Now, let's take a look at what's probably the most common case to reduce the horizontal distance observed at the observation station, the stand station, using the elevation factor. The error regime is very different. Look at this. The worst error is 16.5 millimeters. It's positive everywhere. It goes from 16.6 to 14.7. This is dramatically biased positive. And remember, this is on a 1,000-meter long line and 100-meter high difference between the stations. So it's not a realistic example. I'll show you a realistic example at the end. But the lesson that I'm trying to express right now is that the average of the two horizontal distances that we just looked at works great, full stop. It's for any conceivable distance that a surveyor would ever use, reducing the horizontal distance average is completely dependable. That cannot be said for reducing the horizontal distance from the observation station. You see it right here. A 15-millimeter mistake is surely unacceptable. Of course, the same holds true reducing the reciprocal horizontal distance. This would be the distance from B to A. And I think it's kind of interesting to notice on the left-hand pane that those errors are not exactly the negative as the ones for the forward direction. That's because the two horizontal planes are not parallel to each other. And so they have slightly different error characteristics. The shapes of the error curves are not the same. But here, now notice all of the mistakes, all the errors, they're all negative. This is because the horizontal distance from B to A is less than the average, and the horizontal distance from A to B is greater than the average. That's why these are all positive. Right. So in neither case, with this very extreme and unrealistically extreme example, these are really unacceptable results. Here we're looking at what do you get if you reduce the slope distance itself by multiplication with the elevation factor, and the answer is you get rubbish. Look at these errors that are on the order of 5 meters. 5-meter mistake. The theory behind the elevation factor assumes we are reducing a horizontal distance. The slope distance will be different from the size of the horizontal distances basically by the change in height, proportionally to the change in height. If you've got a 1 millimeter difference in the change in height, you're going to get a 1 millimeter mistake here because of the triangle inequality. The length of the hypotenuse is greater than the sum of the two sides. And so this is never acceptable under any circumstances, as far as I'm concerned. Reducing the slope distance by multiplication with the elevation factor always introduces really bad errors, and it's entirely avoidable. So there's no reason to ever do it, and there's very good reasons not to do it. All right, now, what if we reduce using the formula that goes to the chord? Well, this looks very similar to what we get when we reduce the average horizontal distance, but notice that for 45 degrees, the error is actually 10 times better. That's great, but it was already in the thousandths. Now it's in the tens of thousandths. So this is just packing more angels on the head of the pin. More to the point is that the span of the errors in all cases, it goes from plus 1 millimeter to minus 1 millimeter, and that was the same for the average horizontal distances. So these work more or less as well as one or the other. This one, to a mathematician, this one's better, but they're basically the same. However, the average horizontal distance is not always available. It's available when we have reciprocally observed baselines like a control survey. But if we're not reciprocally observing the baselines, we don't have all the information we need to compute the average horizontal distance. This, on the other hand, is always available because we always have the slope distance. So this is very robust, and the information that it needs is always available. So this is always a good choice. This is what we get when we reduce using the formula where we go to d sub e, the arc. This is an interesting example of finite precision arithmetic. We see this fuzz on the iso lines, and at 45 degrees, something horrible seems to have happened here. What's going on is that the implementation of the arc cosine function is based upon a truncated infinite series for the arc cosine. And the NumPy implementation for the double precision floating point arithmetic that's implemented in Python doesn't have enough high order terms to represent the values very cleanly. And we're seeing the truncation and round off errors creeping in. Then for the center pane, it would appear that perhaps we've lost all precision altogether. That's not the case. Let's take a look at the histogram of the errors for the central pane. It's right here, and they're fine. This looks essentially like the histogram I showed you before. And so what's happened here is not that the computation produced garbage, that it just completely came unstuck. What did happen is that it lost correlation both with latitude and with height. So the answers that we're getting out of it, they're just fine. You see them here. But they're not correlated with latitude or with height. Is that a problem? I can't think of any reason why that would be a problem. So this, in my mind, this doesn't disqualify the second method at all. It just happens to be an interesting example of how a computer can give you sort of unpredictable results when it runs out of precision. So I've claimed that that's the reason. Let me prove to you that it really was. So I reran that example in Python, but using an extended precision arithmetic package. And I computed the answers with 25 digits of precision instead of the like 16 or so that you get with double precision. And as you can see, the 45-degree case, it basically looks fine. There's a little bit of noise on the ISO line for 0. But the rest of it cleaned up nicely. So absolutely, that was the problem. All right, well, in summary, when we're reducing with the elevation factor, my advice is don't reduce the slope distance, full stop. It's error prone and there's better ways to do it. We can reduce either the horizontal distances that we want, no problem. And so I'm talking about the horizontal distance from A to B or the reciprocal distance from the horizontal distance from B to A. We've been doing that successfully for decades. And that 16 millimeter mistake, I'm going to show you what it's like. What is that error when the line is a more realistic length in just one moment? And without showing you the details, I'll just tell you it's fine. So standard practice works perfectly good. But if someone is working on a control survey where really long lines are being observed, then that would not be a good practice. We saw that error increased up to 16 millimeters on a 1,000-meter line, and that's terrible. On the next slide, I'll show you sort of where the cutoff point is. So in standard practice, yeah, it's fine. Reducing the observed horizontal distances works just fine. In all cases, reducing the average of the reciprocally observed horizontal distance is great. Likewise, the formula that reduces slope distance to the arc is fine, although it becomes numerically unstable a little bit when we're working at azimuths close to 45 degrees. And in all cases, reducing slope distance to the chord, the first formula, it works great. It's very robust. And it's just a champ. So for the common practice of reducing the observed horizontal distances, where's the cutoff? And by that, what I mean is, at what distance, what length of baseline will the error achieve about a millimeter or so? So the error contours that you see are, excuse me, that's with a baseline length of 500 meters, and the forward station is 10 meters higher than the observation station. And the errors here are around a millimeter in broad strokes. So a 500-meter line is, it's more than 1,500 feet. That's a really long line. And so if we're getting around 1 millimeter of error for lines that are less than 5 millimeters, I think that's excellent evidence that reducing the horizontal distance that we're getting from the stand station to the forward station, it's just fine in the vast majority of instances. All right. So I will end with some references in case you want to look up the background theory more carefully, see what other people have written about this. If you made it this far, I'd like to thank you very much for watching the entire series. This is where this series comes to a close. And so, again, thank you very much for watching. Take care.